Young participants of our fiber fuse demonstration often ask the following questions. Is this fiber no longer usable? How much does this broken fiber cost? They sound childish, but we need profound background knowledge to give them sincere answers to stimulate their interest. Let's start this video with these questions. The fiber we use in the demonstration is categorized as a single-mode optical fiber for optical communication, made of silica glass. After a single passage of a fiber fuse, the fiber core is catastrophically destroyed and is no longer able to propagate light. A 1 kilometer reel of this fiber costs about $550. We use about 25 meters per demonstration, costing $14. It sounds cheap in this case. However, if we shift our view to optical communication industry, the expenses for optical fibers is many orders of magnitude greater. For the administrators of optical fiber networks, it would be a nightmare to have a break in a cable somewhere. You may recall the eruption of a submarine volcano near Tonga in January 2022, which caused a break in the submarine fiber optic cable to Tonga and a subsequent long period of isolation from the world. Engineers in the industry are updating and controlling their systems to meet the increasing demand for data transmission and avoid various troubles, including fiber fuses. Then, how is a fiber fuse initiated in silica glass optical fibers? Silica glasses used for long-haul optical transmissions are extremely transparent because we need to deliver optical signals as far as possible. Therefore, the fibers allow fairly strong light to propagate without generating heat. However, the situation changes drastically when the fiber is heated to more than 1,000 degrees Celsius. A tiny portion of the glass is deoxidized and absorbs the light energy to generate heat. It accelerates the deoxidation to enhance the subsequent light absorption. This loop causes a rapid temperature increase at the center of the fiber, which is 10 micrometers in diameter. When the temperature reaches several thousand degrees Celsius, the central part evaporates and gets enclosed by glass melt, moving toward the light source through the fiber core. This is what we call a fiber fuse. We often heat optical fibers to more than 1,000 degrees Celsius when we connect a pair of silica glass fibers with a fusion splicer. This device heats the butted ends of two optical fibers through arc discharge. If we let a strong light pass through the joint, a fiber fuse is initiated immediately. Without any special devices, we can heat the fiber with a high absorbance material irradiated by the outgoing laser beam from the fiber end. In this video, a fiber end is pressed against a glass piece containing cobalt oxide. Since the glass piece melts to cover the fiber end, the center of the silica fiber can be efficiently heated to evaporate and generate a fiber fuse. Let's watch an ultra-slow motion video of a similar configuration. Cobalt oxide powder on the fiber end surface absorbs the outgoing laser light and emits weak light. The light spot moves slowly to the undersurface of the fiber, showing the cobalt powder melts the glass and penetrates the fiber end. After reaching a depth of 0.3 millimeters, it begins to emit a strong light and run away immediately. Consequently, in order to initiate a fiber fuse, we have to heat the inside of silica glass fiber to let it convert the light energy to heat. Now, you may notice that fiber fuse is not a problem that can be seen only in the optical communication industry. Nowadays, we have many devices in which strong laser beams are delivered through optical fibers, and we sometimes hear about troubles with sudden interruption of light delivery. Although we cannot definitively say that they are related to fiber fuses, we can get some hints from the knowledge of fiber fuses accumulated since the early stage of optical communication industry. Please read Chapter 7 of this book if you would like to learn more.